Hello, can you hear me?
Yeah, I can hear you. Yeah. So you are having any question?
Yeah. Can you hold on.
Yeah.
Okay.
Yeah.
Yeah, so going back to that, so
Data
scroll
sheet.
up a little bit. What were the two things that you cleared first? So like after the I2C clock enable, I don't think I followed that. Like no, in the above part. Yeah. So you did the clock enable for the I2C. Then you set I2C clock source as the system clock.
Yeah.
What was the bottom two lines for the
Okay. So this is to reset the whole peripheral. To
oh,
reset. So if you open this, let me take it to you. RCC, RCC registers, and we go to AHP res. So as you can see, so we have multiple register ASB, RSTR. Okay, so basically those are reset registers. Okay, and you can reset different peripherals. You can use reset DMA, DMA2. Okay, which one we are using? We are using APB1 RSTR. So we are using APB. So this is APB1 RST1R.
okay.
Okay. So as you can see, you can reset USOR2, you can reset timer, you can reset UART4. Where is the I2C one? So this is the I2C one reset, bit number 20. Okay. So as you can see, so we are resetting the I2C. So basically what the reset does, okay, like let's suppose you want to play a game from the very start. What you do, you just turn off your PC and restart the game. So it's basically just like that. Okay. So let's suppose if you have any software and you made very some kind of changes that you cannot go back and pick and choose each one by one. So basically what you do, you just simply uninstall the software and reinstall a fresh copy. Basically what this reset does, it basically resets all the registers which is available in chapter number 39. It resets all the registers to 0, to reset value, to very fresh. Okay,
Okay.
got it?
Yeah,
Yeah.
that makes sense
Okay.
actually. Yeah, yeah,
Yeah.
yeah. Okay.
Okay. So basically, first we are setting that bit and then we are resetting that bit.
Why do you have to
Although,
set it? Why can't you just reset it?
but either it says basically first we need to reset it and then we need to, otherwise I think this line won't make any difference. Only this line will work fine. Okay, because it says if we write 0, it will have no effect. Okay, so I just wrote that line in order to make sure that everything works fine. Okay, I'm not
Okay.
just playing
I
without
was
any
just
clues.
curious. Okay.
Yeah.
Okay.
Yeah.
All right. And then so then after that you
Yeah. So basically so
wait, why are
these
you sorry,
are,
why are you disabling it?
yeah, now we are dealing with the actual I2C register. Okay,
Why are we
so
disabling it?
I have wrote it wrong way. Basically, we are disable I2C communication.
Well, yeah, but
Okay.
why are
Okay.
we
So
disabling
it's not actually disable. It's like not enable communication, not start the communication while we are configuring the uh, parameters. Okay.
So what
First, we need
happens
to,
if you start modifying that while before without clearing it or without disabling it?
yeah, yeah. So basically it's like a wall. Yeah. So first we are configuring all the things, then we will enable all the wall. So this is like a wall. So you don't have necessary, you don't have only one switch inside inside the microcontroller you have many switches. Okay, so basically this is a disable switch. You can enable the
Do you know how we
so
can
what
make you louder? You sound very quiet. Is there a way to make you louder?
okay, now is it better now?
Oh, much better. Yeah, yeah, yeah.
Okay,
Okay.
so basically when you reset this bit, this will reset all the registers. Okay, but when you use PE bit, okay, you can disable the I2C communication, but the all the configuration registers, they will stay the same. Okay, and the data sheet of the nuclear board says that if you want to configure the timings and if you want to configure the I2C, first you need to disable the transmission. Okay, and then after configuring all the stuff, okay, you can re-enable it. Got my point?
Yeah.
Yeah, so that is the thing. So first we are disabling it, okay, and then we are enabling the analog filters. Okay, so basically those we are not defined, they are just hardware, they are part of just hardware. Some microcontrollers have those filters, some don't. Okay, and this is the
Okay.
error detection interrupt. So you have multiple interrupt. If you go into 39 registers, so this is the first registers, and these are multiple registers. Okay, so these are interrupts. So TXIE interrupt, RXIE interrupt, stop, not acknowledge interrupt, transmission complete interrupt, error occurring interrupt. So these are many interrupts. Okay, you can enable all the interrupt based on your requirement. But since we are not using an interrupt based system, okay, as you can see, so since we are not using any interrupt, so I am just disabling all the interrupt. Only
Okay.
the error based interrupt, I just kept it on error based interrupt in case if the communication gets stuck. Okay. For example, there was a communication between the nuclear board and the IC. Okay. And we just started the communication with the address. Okay. And suddenly you press the reset button on the microcontroller. Okay, so what this will do, you have interrupted a transaction which was going on. Okay, now this thing will create an interrupt for the nuclear board to, so nuclear board can know that the communication, that it has received an error during communication. Okay, so these are just different bits you can play with. So I am just enabling the error interrupt bit, error detection bit. Okay,
Okay.
and I have enabling the clock stretch. Okay, so what is the clock stretch? So clock stretching means you give access to slave that it can stretch the SCL clock. Okay, um, if you open the A8 quickly, so in the end it says the EEPROM requires 5 millisecond delay after writing data before any other operation can occur. Okay, so when we write some data, okay, and so we need to give it 5 millisecond delay before we can do any operation, like we can do any second write operation or read operation. We need to give it 5 millisecond delay. Okay, because when we give it a command to write a data, during that 5 millisecond, it takes the data and write to its own registers. Okay, because it has its own memory. Okay, it takes time. So during that time, the slave can stretch the SCL clock. Okay, usually the clock is going on. Usually the clock is going on like this. Okay, but slave can stretch the SCL clock before generating an acknowledge. Okay, because first it needs to write the data in its memory first before generating an acknowledge. Okay, so slave can stretch this clock, so we give this flexibility to slave. So this is no stretch, so we are clearing it, means we are enabling the stretching. You go to the reference manual. Yeah. So you see, so bit number 17, if we clear this, that means we are enabling the clock stretching. Okay, and now we need to define the timings. Okay, as you can see in the data sheet of if you go to the very first, so you can see 24LC256, the maximum clock it can operate, which is the 400 kilohertz. Okay, so there are three operations of I2C. One is the low speed, which is the 100 kilohertz. One is the high speed, that is the 400 kilohertz, and one is the highest speed, which is the 1.2 megahertz. Okay, but the maximum it can operate on two clocks. Okay, 100 kilohertz and 400 kilohertz, but I am using 100 kilohertz only. Okay, because that works for most I2C ICs. Okay, so now we go into the timing register. Go here, I2C register. We need to go into timing register. So in timing registers, um, so we are operating the system clock at 80 megahertz. Okay, we are of 80 megahertz. So this is 80 megahertz, and we want to run I2C on 100 kilohertz. Divide by 100, and kilo means 3. Okay, so we get the value of 800. Um, oh yeah, we have a prescaler as well. Okay, so 800, and I am using a prescaler of 8 as well. So divide by 8, so that means we get the value of 100. Okay, so so the clock period, like from one end to the another end. Okay, we need to give SCL value 200. Okay, and prescaler is 8. Okay, so that is the thing I am doing. So first I am clearing all the prescaler bit, PRESC, that means prescaler. First I am disabling the prescaler bits. Okay, and then I am writing prescaler value 7, which is, 7 is not exactly 7, so 8 minus 1 is equal to 7. Okay, so basically I am writing the prescaler to be 8. Okay, so what this prescaler does, system clock is 80 megahertz with prescaler value 7. We are making the I2C clock reduced to 10 megahertz. Okay,
Oh, okay. Is there a reason why we do that instead of just setting it to 10 to begin with?
yeah, we do this to make different clocks, like for our I2C operation. Okay, so let's suppose you want to make it run very slow, because you see the data sheet says maximum clock. Okay, data sheet says maximum clock, so it did not mention any minimum clock. So that means you can run it on 100 hertz, 200 hertz. So in order to make 200 hertz, you need to divide it, you need to divide the clock. Okay, so prescaler is there for you um, to help you out. Okay, So as you can see, this timing register. So these last four bits, these are the prescaler bits. Okay. So these are prescaler bit, and it starts from bit number 28. Okay. So basically, to make things very simple, I am using the prescaler. So
But is
basically,
there
we
what I
have,
mean? Sorry, what I mean is there a reason you're using 10 megahertz?
yeah. So basically, I have just pre-scaled the clock from 80 to 10 now. Okay. And I want to run it on 100 kilohertz clock. Okay. Now I will
Like
give
you want to
the
run the
SCL.
I2C, you want to run the I2C on
Yeah,
100 kilohertz.
yeah, 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 yeah.
Okay, okay.
Okay. So
So
basically,
first you set the
yeah,
SCL to 10
yeah,
megahertz. You set it to 10 meg.
yeah, 10 mega. No, basically, mm, if I can show you
Because
the
you set the system clock to 80.
yeah,
Is there a reason system clock was set to 80 or is that like predefined value?
yeah, 80. How did we set to 80? Yeah. So we go into, so you see, this is, if you see here 80, so 80 is the maximum clock. If you set HCI and use PLL, and you can set it to maximum 80.
Okay.
Yeah. So your microcontroller can maximum give you 80 megahertz clock. Okay. So that is what I am using, 80 megahertz. Okay. So,
But why is it
so
80? Like why if we're just gonna bring it down, why set it to 80 to begin with?
you can use 40 as well.
Okay, so you just picked it kind of arbitrarily, or is there anything else that uses the clock or just the I2C? Like why not set it to 100 kilo to begin with if that's what we're gonna use?
100 kilo. No, we cannot use 100 kilo here directly here.
Why?
Okay, because this clock control is not just only for I2C. Okay, there is a whole CPU working as well. The CPU, it has its own memory as well. It has its own CPU registers as well. Okay, so it needs to have a higher clock. Okay, with higher clock, the you can do things, like it's simple. The more clock you have, the mm, the more easier, not more easier, the more less time one instruction will take to execute. Okay, so usually we make it to run on maximum clock. Okay, unless we want to do some energy saving things. Okay, like a low power application, like if we want to operate on some kind of battery. Okay, then we use a reduced clock like 1 megahertz or 2 megahertz, like this, because the more clock you have, the more cycles you will have in one period. Okay, and it will take more current. Okay, but usually we tend to run the microcontroller on its maximum clock. Okay,
Okay.
because more people know about it. Okay,
Oh,
if you
okay,
if
okay.
you if you use 24 megahertz clock, okay, and your code goes to some developer, he will assume that you will be using
Understood.
maximum clock. Yeah,
Understood. So it's more common to just set it at max and then bring it down to what you need rather than setting it to something else.
yeah, that is the issue.
Okay, understood. And then is there a reason you bring it? Why do you use the prescaler to bring it down to 10 meg and then divide it by 100 again? That I
Yeah,
don't understand.
so I am running the clock on 100 kilohertz.
No, but
Okay,
okay. First you use the prescaler to bring it down to 10 megahertz, right?
yeah,
Right?
yeah,
10 megahertz.
yeah, yes.
Then what do you do to bring it down to 100 kilohertz?
Okay, so the maximum clock the EEPROM can work on, which is the 400 kilohertz. Okay, I am using 100 kilohertz, which is the most common and most basic I2C communication. If you go into Google,
No, no, no.
uh,
That's not my question. I
I2C,
understand you need it to be at 100. I get that. I get that. That's not my issue.
Yeah, yeah, you can directly, we can directly, so if we skip the prescaler, okay, we can directly use the timing registers to directly bring, like from, for example, I can use
80 meg to
80 megahertz directly, and I can use 800, and it
yeah,
will
so why
give
not do
me,
that? Why did you use prescaler first?
yeah, we can totally do that.
Okay. So there's multiple
Okay.
ways to achieve the same thing.
Yes, multiple ways, but we need to check this 800 can fit in, this 800 can fit within the bits. Let me show you what I mean.
Oh, okay. Okay, okay.
Yeah. Okay. So where is the timing register? As you can see, this is SCL low and this is SCL high.
Mm-hmm.
Okay.
Also,
So as,
800 may not necessarily fit. I understand.
yeah,
In the
800
bits.
may not.
Okay,
So
so that's why you use prescaler to bring it down. So because we're limited by bits and embedded, we have to sometimes do multiple steps to like,
yeah.
okay, I follow, I
Yeah,
follow.
so that is the reason.
Yeah,
So as you can see, this is the maximum 8 bits. So maximum 8 bits, maximum value is 256. Okay.
understood.
But if we divide the 800
Wait, sorry,
into,
what is 8 bits? Oh, the timing are the time.
yeah,
Yeah, yeah, yeah. Okay.
yeah, okay. Let me quickly. So you have SCL low period and SCL high period. Okay. So the total from here to here, it will be 800 value. Okay. So 400 will be lower and 400 value will be higher. Okay. So we have two registers. As you can see, this is SCL low and this is SCL high. Okay. And since SCL low is maximum 8 bits restricted, okay, so it can have maximum value of 256. We cannot write 400 to it. You got my point?
Yeah, I got you.
And similarly, the higher one also can get 256 maximum value, but we need to give it 400 to make it SCL low period and high period. We cannot do that. So that's why I am using the prescaler. We use the prescaler because first it's available there and it's easier to use, and we can make things simple instead of making them complicated. Okay. So that's how I am doing these things. So
That makes
10
sense to me.
megahertz and a 10 megahertz, if I divide it by 100, I get the 100 kilohertz clock. Okay. And since we get the 100 for whole SCL, so we need to divide it by 2 to get the half period of SCL low and half period of SCL high. Okay. So I am writing 49 as SCL low period and 49 as SCL high period. Okay. And shifting it by 8 because the SCL high is available on bit number 8. As you can see, so this is bit number 8 and SCL high value is available on 8 to 15 bits. Okay. So that is what I'm doing. Okay, now this is some very specific thing according to datasheet. So this is SDA setup time and SDA hold time. Okay, I think you should just have these values. Okay, basically what these timings are, when I wrote their definition. Okay, how can I show it to you? Okay, we will get back to this point later. Okay, so I will tell you how we are setting these values. Okay, at least the 100 kilohertz clock, your
Yeah, that makes
concept is
sense.
clear.
Yeah.
Okay, so yeah, and this is the OAR and OAR2 register. So basically, this is the on address register. Okay, so we are just setting the on address here, and we are enabling the on address in case if you want to do the
Slave.
slave configuration. Okay,
Yes,
so
understood.
but we are not using these. Okay, so this is just for there for the configuration. Okay, and now we have the I2C CR2 register. Okay, so this bit CR2 address 10 ADD 10. So we are disabling the 10-bit address. We are using only 7-bit address mode. So basically there are two address modes, 7-bit address and 10-bit address. So we are using only 7-bit address mode. We will clear that bit. If you want me to show that CR2 register, so you quickly go there. This is the 10-bit address. This is that bit, and we are clearing that bit to make the use of 7-bit address because our IC work on 7-bit address. Okay, and then this is the auto end. Okay, so this is the bit when you send specific number of bytes on the transmitter, you need to create a stop condition. I told you earlier that the transmitter or the master needs to create a start condition and stop condition. Okay, so what? There is function in the CR2 which says n bytes. Okay, so n bytes means how many bytes you want to write to the slave device. Okay, so you write that number of bytes value to these bits. Okay, let's suppose you want to write 3 bytes or 2 bytes, so you write 3 value to these bits. Okay, and there is an auto. Where is the auto end? It's available in CR2. Okay, bit number 25. Okay, yeah, this is the auto end. So basically what this auto end does, it creates a stop condition automatically when you send a specific number of bytes. Okay, so that is the thing. And this is the not acknowledge. So we will change this bit during communication. Okay, so let's just ignore those bits, and then we are enabling the I2C communication. Okay, so I will explain this not acknowledge. I told you when not acknowledge bit we need to set it one. Okay, so when the master receives data, okay, let's suppose he master wants to receive 5 bits. Okay, so when master will receive first byte, it will send an acknowledgement to slave. When it will receive second byte, it will send acknowledgement. When it will receive third byte, it will send acknowledgement. When fourth byte will send acknowledgement. But when it will receive fifth and last byte, the master will not acknowledge it. Instead, it will send not acknowledge. Okay. So basically, when we don't send acknowledge, it's same means that this is not acknowledged. Okay. Or instead of acknowledge, the master just terminates the communication. It just creates this
So does it
stop.
send a no acknowledge? Is that what you're saying?
Yeah, so basically not acknowledge means so basically not sending an acknowledge means not acknowledge, NAC. Okay,
Okay.
But this is the case when we use I2C in slave mode. So this is doesn't concern as well as for us. Okay. So yeah, this is just for there for like a understanding purpose. So I just wrote it for my own understanding,
Okay.
and now we are enabling it. Okay. Now see, so this is just for the initialization part. Okay. Now we have functions for I2C start condition. Okay. And I2C stop condition, I2C wait line idle. So that in that function we check if the line is busy or not. Okay. For example, if you have two or three master, okay, and one master is communicating with EEPROM, this second master needs to wait until first master completes its communication. Okay. So basically we use this busy flag to check if the line is idle or is it busy. Okay. And this is the I2C write data function, and this is I2C read data function. Okay. So let's go quickly go with the I2C start function. Okay. So in order to create the start condition, first we read the CR2 register into a temporary value, into a temporary register. Okay. So first we read the whole register. So we will deal everything with CR2 now. Okay. So CR1 is just for configuration, but for actual transaction, you will use CR2. Okay. So first you will read CR2. Okay. And then you will clear all the bits, which is the SADD, which is the slave device address. You will clear the number of bytes that you want to write. You will clear the reload. You will clear the auto end. You will clear the read and write bit. You will clear the I2C start and I2C stop. Okay, so you will clear all these bits first, and then you will choose your own configuration. Okay, for example, this I2C start has three parameters. One is the device address, second is the size of the bits, okay, and third is the direction. So direction means if you want to write to slave or read from slave. Okay. So you will use this parameter as a direction. Okay. So first we will clear all these bits, then we will choose direction. Okay. So based on direction, so direction is read from slave. If you open this one, so basically it's just 1 and 0. Okay. So read from slave is 1 and write to slave is 0. Okay. So if you want to read from this slave, you need to make the read and write bit to 1. Otherwise, you need to make that bit 0 or clear that bit. Okay. Now, now in CR2, we need to add the address. Where we get this address, we will send this address into this function. Okay. We will send the address into SADD bits. Let me quickly show you. So these are SADD bits. Okay. So these are bits for the slave address. Okay. So these are the 0 to 9 SADD bits, slave address bits. Okay. So you write 7 bits here to tell the master what is the address of the device. Okay. And this is the RDWRN, which is the read and write bit. If you keep it 0, that means we want to write the transfer, and if you keep it 1, that means we want to do the read operation.
Okay.
Okay. Similarly, if we go above, you see this is the start condition. If we make it 1, we will create a start condition. And this is for stop condition. Okay, when we make it 1, the stop generation occurs after current byte transfer, and this is the NAC, which is the not acknowledged, but this is for the slave mode. Since we are not using any slave mode, so we are not understanding. And this is the n bytes. Okay, so n bytes means the number of bytes that we want to send or receive. Okay, so that function is doing the same. So this size parameter will be shifted by 16-bit because it's available on 16 to 23. Okay, and we are modifying these bits, okay, with size. Okay, so
Okay.
all this we have saved in the temporary register. Okay, and then we create the start bit. Okay, and then we enable the start bit and restore and write it into this one. Okay, and after the everything is done, we just write the whole register to CR2 directly. Okay, so you will have question here. What is the question? Why you use this temporary register instead of directly manipulating the CR2? Okay,
Right.
so you will have this question. So why we are doing this? Because if we directly write the I2C start here, okay, it will start the communication, but how will we send the number of bytes? How will we modify the read and write bit? How will we modify the number of bytes? Okay, so basically first we read the whole contents of like 32 bits, okay, and save them into our own register, our temporary register, and then we manipulate things into our temporary register. Okay, we are not
Oh, and then once everything is
manipulating.
fully read, then you start
Yeah,
to
once
communicate.
everything is fully configured, then we just write it to CR2. Then everything goes into that register and it works fine. If we write start condition directly to CR2, it will start the condition, but it does not have the correct address because we have not fed it, and it does not have the correct number of bytes. It might not have the current, not have the read and write bit also, like if you want to read it or write it. Okay, so that is how we are doing things. This is just for the safety purpose, I just kept it. You can remove it because these are just comments. You can remove all of them. Okay,
Okay.
so to make things simple.
Okay.
So this is the start condition. So we have created a start condition.
Yeah.
Okay, now we go into stop
Sir,
condition.
our time
Yeah.
is running out. Why don't we stop here and then we can continue this on like tonight, IST time?
Okay. Yeah, we can do it, man.
Okay. Because it's gonna start to get like late for me. Can we do around like uh let's say like 10:30 p.m. IST?
10:30 will be my 11. Okay, yeah, 11 is fine.
Yeah, okay, sounds good. I'll confirm with Ram and then we can set that up. But then yeah, we can
Okay, so
do
we
some.
have just 1 minute left. During that 1 minute, we just use the stop condition. So we will use the CR2 register. Okay, and simply we use a stop condition directly. Okay, so
Mhm.
it will generate the stop condition after the current byte has transferred. Okay,
Okay.
and we will wait for the transmission to be stopped. Okay, so we will keep the system here, we will keep the CPU busy here until the communication is actually stopped, because when we create a stop condition during the byte transfer, it does not go stop directly. It needs to finish that byte. Okay, then it will do the stopping. You cannot interrupt the transmission in the middle.
Okay.
That is the stop condition. Okay, and meanwhile you can watch a video. I will send you, okay, a link. You can get some more basic information about I2C as well. Okay, so
Sure.